in this example, we have a mass of 1 kg suspended by 2 taut strings, as shown in the diagram. We've got tension for each of the strings, and we also have weight as our 3 forces acting on the object. So our force diagram looks very much similar to the diagram above. We've got a string going horizontal to the right. Let's call that tension 1. We've got string 2 going up for 42 degrees, tension 2, and we've got the mass or weight heading straight down. Now, because this is in equilibrium and it's not moving, it means that our triangle of forces is in play. So there's our force vector diagram, part A. Part B, by resolving vectors into I and j components, determine the magnitudes of T1 and T2 respectively. So we transform that into a triangle of forces when we put T1, T2, and the weight together. We do create a triangle because it is in equilibrium, and that is 42 degrees. Now, in terms of I, j, and k, looking at the vectors up the top here, we can say that T1 is going to be only I vectors. So T1 is going to be T1I. Just to say that T1 without the tilde on it is the magnitude of T1. Now, T2, well, that's going to be using cos and sine because it has some i's and some j's. It's also going in the opposite direction of I. It's going to the left, whereas I is going to the right. So we'll go T2 cos 42 degrees I, and we'll actually say it's negative because it's going left, plus T2 sine 42j. And then we'll say weight is g, or negative g, because that's our acceleration towards the ground. And that's also acting in just the direction of j. So the horizontal component of T2, that will need to be equal to this, and the vertical component, that these two values need to be equal, otherwise we're not in equilibrium. So working on the yellow first, we can say that T2 sine 42 is equal to g, not negative g, because they need to balance each other out. Okay, so if we divide both sides by sine 42, we will get the magnitude, the vertical component of the second row. And g in this case is negative 9.8, or just 9.8, because we're after the magnitude of it anyway. So when you put 9.8 over sine 42 into the calculator, it's 14.6 newtons. Now that we know T2, we can evaluate T1, because T1 over the blue highlighter is equal to negative T2 cos 42. So that means we can take this and go, well, T1 is equal to T2 cos 42, and T2 is 14.6 cos 42, and that equals 10.9. And that's the force on the rope.